Welcome back to the Deep Dive, where we take the most complex strategic roadmaps and, well, we try to make them crystal clear for you.
And today, we're tackling a big one.
We really are. We're diving into a document that maps out nothing less than the future of automotive manufacturing all the way out to 2040. This is a very dense, very professional report, and our mission is to unpack what it all means.
That's right. This is the Digital and Intelligent Equipment Technology Roadmap. And, we're not just talking about adding a few more robots to the line. This is a complete paradigm shift.
Right.
The report talks about something it calls digital and intelligent equipment, or if you look at the original term, YOCHACH.
And when I hear that, I'm thinking, high-speed robotics, maybe some fancy new automated vehicles. But the language in here is, well, it's more profound. It talks about an intelligent body.
Mhm.
Like, wait, what is that?
That's the core concept, is the difference between a tool that follows instructions and an entity that can, well, grow. Yes. The roadmap defines this future equipment as an evolving, intelligent body. It's not just programmed. It has 5 core functions that create this strategic closed loop. Self-perception, self-learning, self-decision-making, self-execution, and this is the big one, self-evolution.
Self-evolution. So the machine is actively improving itself in real time without a human stepping in.
Exactly. Using data to continuously get better on its own.
Yeah,
It's a staggering claim.
it really is. Now, before we get into the nuts and bolts, the roadmap uses a grading system to measure all this progress, right? The IME levels.
It does, absolutely.
Can you just give us a quick overview of what that is? I think it'll help frame the whole discussion.
Of course. IME stands for Equipment Intelligence Maturity Levels. It's a scale.
Yeah.
So IME 1 is basically, simple, unconnected digital equipment.
Right.
And it goes all the way up to IME 4, which is that full autonomy, that self-evolution we were just talking about.
So the whole point of this 20-year plan is to push the industry from, say, IME 1 or 2 all the way to that IME 4 future.
Precisely. It gives us a measurable way to track progress.
Okay, so let's unpack this. Our goal today is to look at why this shift is so critical, where we stand right now globally, and then walk through the roadmap itself, 2030, 2035, and 2040, to see how we get from here to there. So let's start at the very beginning. Why is this massive overhaul of the factory floor happening right now? What are the pressures forcing everyone to think so far ahead to 2040 instead of just, the next quarter?
Well, the sources are really clear that it's coming from all sides. It's not just about making things cheaper anymore.
Right.
It's about making totally different things in totally different ways and at a speed that current factories just can't handle. The document lays out 4 major trends that are really driving this.
Let's start with the customer, because I have to imagine the shift to new energy vehicles to NEVs has completely changed what people expect.
It's completely changed the game. And that brings us to trend 1, mass personalization and customization.
The end of the one-size-fits-all car?
Exactly. People want endless configurations, different battery sizes, interiors, you name it. And traditional assembly lines, they were built for rigidity, for churning out thousands of identical cars. That model just breaks when you introduce this much variety.
So the line needs to be able to switch from building, I don't know, a high-end sedan to a basic van, maybe even on the same line, without shutting down for hours to retool.
That's the dream. The equipment has to be able to recognize what's coming, adapt its own process, and execute it flawlessly. If it can't reconfigure itself on the fly, mass customization just isn't profitable.
Okay, that makes sense. That brings us to the second big trend, which I imagine has huge implications everywhere.
We've seen
Sustainability.
huge. Trend 2 is agile green manufacturing. The agile part is about market response, but it's now tied directly to extreme environmental performance.
And this isn't just about the car being electric, is it?
Not at all. It's about the machine that built the car. The whole life cycle of the equipment, its design, its operation, its recycling, has to meet these really tough standards for low energy use, low carbon emissions, and high resource utilization.
That sounds incredibly expensive to implement. How does a smarter machine help with the green part?
Through precision. Old school manufacturing has a lot of waste built-in scrap material, wasted heat, motors running harder than they need to.
Right, the tolerances.
Exactly.
Yeah.
An intelligent machine uses adaptive control. It monitors itself in real time and eliminates that waste. It adjusts power use based on the actual load, optimizes cutting paths down to the micrometer. It can even recover waste heat.
And the roadmap has a specific target for that, doesn't it?
A massive one. A 40% reduction in energy consumption by 2040. This isn't just about being good corporate citizens, it's about global cost leadership.
And all this, the efficiency, the customization, it all runs on data. which I think leads to the next trend, connecting the factory to the whole business.
It does. Trend 3 is R&D supply sales service integration, or PIECE.
Okay, break that down for us.
Think of the equipment not as a dumb tool anymore, but as the central data hub for the whole company. It's not just building the car, it's sensing how it's being built, recording quality data, and feeding that back instantly.
Back to the designers, to the supply chain.
To everyone. R&D can refine the design, the supply chain can manage inventory in real time, service teams can predict maintenance needs. The equipment's intelligence basically sets the speed limit for the entire business.
So it creates this incredibly fast feedback loop.
That's the goal, a closed loop of data collection, analysis, and execution. The quality of that loop determines if a company can pivot fast enough to survive.
And finally, there's the car itself. The materials are changing.
Radically. Trend 4, new processes and materials. We're moving away from just stamping steel. You have things like integrated die casting.
Where they make a huge chunk of the car's body in one single piece.
Exactly. The entire rear cabin, for instance. That requires tools of a scale and precision we've never seen before. And then you have solid-state batteries, carbon fiber composites. All of these demand brand new manufacturing techniques.
So you can't just upgrade the software. You need fundamentally new machines.
You do. The equipment itself has to evolve to handle the physics of the future car.
So to sum it up, the equipment is no longer just a piece of hardware. It has to become this intelligent service unit that drives the whole operation.
That's the strategic conclusion. And it leads to a really important engineering concept here. Equipment resilience.
Resilience. How is that different from just, reliability?
It's a great question. Reliability means the machine works as expected. Resilience means it keeps working or recovers instantly when something unexpected happens.
Ah, okay. So if a sensor goes bad or the quality of a metal sheet is slightly off,
The machine doesn't just shut down and wait for a technician. It figures it out. It compensates, it adjusts, it keeps the line moving. It's about having a self-healing capability, which is absolutely essential if you want zero unplanned downtime.
okay, so the why is clear. Now, where are we today? The roadmap talks about this global duality pattern, a sort of tension between the big international leaders and domestic innovators. Who holds the cards right now?
Well, the established international leaders, they have a really strong grip on the foundational layers. This creates some pretty high barriers to entry.
In what areas specifically?
First, in core components. And we're not just talking about good quality parts. We're talking about the absolute best-in-class stuff. Ultra-high precision sensors for vibration, for displacement, that you need for that micrometer level control.
The things that let the machine feel what it's doing.
Precisely. And also high-end bearings and, crucially, high-performance servo motors. These parts basically define the upper limit of how stable and precise a machine can be.
So they own the building blocks.
They do. Second is their underlying technology architecture. They have decades of data, decades, and they've used it to perfect their industrial operating systems, their software platforms.
So it's not just the hardware, it's the accumulated knowledge baked into the software.
It absolutely is. Third, they control high-end CNC systems, specifically the specialized chips and the really complex multi-axis linkage algorithms. This is what allows for that super dynamic, precise coordination.
Okay. And the final piece.
A mature software ecosystem, a whole integrated world of equipment plus software plus data that just works seamlessly together.
That sounds like a pretty daunting list of advantages. So given all that, where is the domestic industry managing to break through? The report mentioned rich application scenarios.
Yes. The sheer speed and scale of the new energy vehicle market in certain regions provides this incredible testing ground. It forces innovation, and we're seeing huge wins in very specific process-focused equipment. Battery manufacturing is a great example.
Can you give us some hard numbers on that?
Sure. In coaters, which apply the material to the electrodes, precision has improved to within 1%. That's a huge deal for battery performance and reducing waste.
Okay.
In stacking machines, which align the battery layers, they've hit an alignment precision of 0.1 to 0.3 millimeters. That's thinner than a human hair. And doing it at speed boosts efficiency by something like 40%.
That's incredible precision.
And we're seeing new thermal presses for solid-state batteries, which require this insane level of pressure and heat control. So very targeted, very impressive wins.
And what about outside of batteries? I know lightweighting is a huge focus. That brings us to that giant machine.
It does. Lightweight manufacturing. The most famous example is the development of the world's largest 16,000-ton die casting machine. It's what allows for those huge, integrated structural parts.
I have to stop you there. This is something that seems like a contradiction to me. The whole vision is about flexibility and customization, right?
Right.
But building the world's biggest, most specialized machines sounds like the definition of rigidity. How do you square that circle?
That's a fantastic question. And it gets to the heart of what flexibility means now. The press itself, the 16,000-ton machine, yes, it's rigid.
Okay.
But the flexibility is designed into the process around it. It's in the ability to swap out the massive dies and molds really, really quickly. And it's in the intelligent control system that can make tiny real-time adjustments to pressure and temperature to guarantee a perfect part every time. So the flexibility shifts from the machine's body to its tooling and its software brain.
Ah, I see. So the hardware is stable, but the tooling and software are agile. What about joining all these new materials together?
Big advances in laser welding. It's a fundamentally better for this. It's up to 3 times faster than traditional welding. But the real win is in quality. Defect rates are down 90%.
90%.
And the heat-affected zone, the area that gets distorted by the heat, is 5 times smaller. That means less warping, fewer adjustments, and you can join dissimilar materials like steel and aluminum much more reliably.
So despite these wins, where are the big persistent gaps? Where does that reliance on international leaders still hurt?
It's still in those foundational layers. High-end chips, those critical sensors and servo motors. There's still a heavy reliance on imports. But the most critical gap, the one the report really highlights, is data.
The data gap.
It's a chasm. The document states that the data collection coverage rate is currently less than 30% in many domestic firms.
Less than 30%. Wow. So if the future is a machine that learns from data, right now its brain is only getting, what, a third of the sensory input it needs?
That's exactly it. It's operating with severely limited senses. And this is made worse by a weakness in developing their own industrial software and operating systems.
Yeah.
You can have all the application scenarios in the world, but if you can't collect and process the data effectively, you can't turn that scale into real, sustainable intelligence. That 70% data gap, that's the battleground for the next decade.
Okay, that sets the stage perfectly. We know where we're going, the intelligent body. We know where we're starting some pockets of hardware strength. But major software and data weaknesses. The roadmap lays out the path forward with 3 big interdependent pillars.
That's right. These are the building blocks that get us from automation to autonomy.
What are they?
First, flexible and resilient execution. That's about the physical machine. Second, embodied intelligence evolution, giving it a brain and nerves. And third, group collaboration, linking all the smart machines together into a smart factory.
All right, let's start with pillar 1. How does a piece of equipment actually become more flexible, more resilient, and higher performing all at the same time?
It starts with performance optimization, or DOM, pushing the physical limits of precision, speed, and reliability. And the way to do that is by blending new materials and technologies with smart controls.
What kind of materials are we talking about?
Things like carbon fiber for machine structures to make them lighter and stiffer so they can move faster without vibrating. Silicon carbide for more efficient power electronics in the motors.
Okay.
And then you layer the intelligence on top. For instance, the system can monitor its own temperature in real time. Metal expands when it gets hot, right?
Very, throws out the precision.
The machine knows this. It detects the thermal expansion and automatically adjusts the tool pass by a few micrometers to compensate. It's building resilience right into the hardware.
That's the high-end part. What about the flexibility? The roadmap talks a lot about modular design and software-hardware decoupling.
This is the absolute key to making mass customization work. Modular design means building equipment from standardized, interchangeable blocks, like Legos for the factory.
So instead of a custom machine for every car model, you just rearrange the blocks.
Exactly. You reconfigure universal fixtures instead of building new ones. It cuts down on cost and changeover time massively.
And the software-hardware decoupling.
Yeah.
That sounds like a really fundamental shift. Software-defined equipment, SDE.
It's a revolution. For decades, a machine's logic was hardwired into a physical box, a PLC. If you wanted to change what the machine did, you had to physically mess with that box.
Right.
SDE takes that logic and turns it into software that runs on a more general-purpose computer. It's a software-defined PLC.
So it's like updating an app on your phone, but for a giant industrial robot.
That is a perfect analogy. You can add capabilities, integrate new sensors, deploy new AI algorithms with an over-the-air update. And this is supercharged by AIGC AI-generated content. AI can now help design the modules or optimize the process paths, slashing R&D time.
And the final part of this pillar, low carbonization, ties back to that green manufacturing trend.
It does. It's about building environmental performance into the whole life cycle. using recyclable materials in the machine itself. And then during operation, the software is constantly optimizing energy use, reducing scrap, everything we talked about to hit that 40% reduction target.
Okay, so pillar one gave the machine a better body. Pillar two is about giving it the senses and the brain. This is where we get to that autonomous, intelligent body.
Yeah, and it all starts with sensing, all domain perception. Off God said, the machine has to go from having one or two simple sensors to having a whole nervous system.
And what does that nervous system sense?
Everything. The report lists 7 categories of production data. Things like the equipment's own status, its temperature, its vibration, process parameters, pressure, speed, product quality, energy use, safety, even the ambient environment like humidity.
That is an unbelievable amount of data to process. How does it not just get overwhelmed?
By fusing different data types together at the edge, the smart welding robot is a great example. It's not just looking with a laser vision sensor to see the 3D shape of the weld.
Okay.
It's also using an arc sensor to feel the electrical properties of the weld in real time. It fuses those 2 data streams together and can adjust its parameters instantly, boosting the quality acceptance rate from 85% to over 98%.
So once you have all that sensory data, you need somewhere to use it. That brings us to the digital twin, right? Virtual physical coexistence.
Exactly. The digital twin, or DT, is this perfect virtual copy of the physical machine. It's the 3D model combined with that live stream of sensor data. Right now, companies are using DTs to simulate and debug production lines virtually, which cuts down physical setup time by more than 50%.
But a DT is just a mirror, right? For it to be truly intelligent, it needs a brain. Is the idea really to plug a large language model into the factory's digital twin?
That's exactly the idea. The roadmap calls for integrating AI large models with the DT engine. But these aren't going to be like the huge general-purpose models you see online.
They'll be specialized.
Highly specialized. Vertical large models trained just on industrial data, running on small, powerful edge computers right next to the machines.
But the security risk there seems enormous, all that proprietary operational data.
It is, and the roadmap addresses it directly. It calls for using technologies like blockchain to create an unchangeable record of data and something called homomorphic encryption.
Which allows you to do what?
It allows you to train a shared AI model on encrypted data, so companies can collaborate to build better models without ever revealing their secret sauce.
So perception and simulation. It all leads to intelligent decision-making. How close are we to true autonomy?
Right now, we're pretty good at single-function stuff, like a machine adjusting for tool wear on its own. And self-diagnosis is getting really good. These EHM, or equipment health management systems, can predict failures and have already cut unplanned downtime by around 40%.
Which is a huge gain. But the 2040 vision is way beyond that.
It's the holy grail, self-repair and self-evolution. Self-repair is the machine fixing itself, maybe by rerouting a task to a backup component. And self-evolution is the machine learning and creating brand new strategies on its own without a human programmer. That's the ultimate goal.
All right, so we've gone from a single smart machine to now the whole factory as a single smart ecosystem. Pillar 3, group collaboration.
And the foundation for that is just getting everything connected. Equipment networking .perio. You need to link up all the different devices, robots, CNC machines, AGVs on a common platform.
And the report specifically calls out 5G private networks for this. Why 5G?
One word, latency. When you have dozens of robots moving around, a delay of even a few milliseconds can cause a collision. 5G and edge computing allow for that near-instant, millisecond-level local control. Critical commands happen on the factory floor, while the big-picture analysis happens in the cloud.
So that network then enables multi-agent collaboration. It sounds like conducting an orchestra.
It's a great analogy. We're moving away from a linear production line. Machine A finishes, then Machine B starts to do a dynamic, data-driven dance.
And the goal isn't just to optimize one part of the factory, but the entire system.
Exactly. Global dynamic system optimization. That means breaking down the data silos between different workshops, even different factories.
What does that look like in practice?
It means if the sales team sees a sudden spike in demand for one car model, the entire system, from material ordering to the robots on the floor to the energy schedule, autonomously reorganizes itself to meet that demand in the most efficient way possible, optimizing for quality, cost, delivery, and safety all at once.
And the final piece of this puzzle is the most futuristic one. Embodied intelligent robots. Humanoid robots on the line.
Yes, that's part of it. We're seeing them in demonstration phases now, doing complex assembly or handling parts. But the roadmap is also very realistic about the challenges.
It's not just the cost, is it?
No, cost is a big one, but the tech hurdles are bigger. They still struggle with complex, unpredictable environments. And their ability to generalize, to learn one task and apply that skill to another, is still very limited. We also just don't have the safety and ethical frameworks in place for what the report called human-machine cooperative evolution.
Which is more than just a human and a robot working side by side.
Much more. It's about them adapting to each other in real time. The
Hmm.
robot senses the human is slowing down and picks up the slack. Or the human adjusts their workflow based on what the robot is doing. It's a true symbiotic collaboration.
Okay, this roadmap is incredibly detailed with very clear metric-driven goals for each phase. As we walk through this timeline, 2030, 2035, 2040, we're basically tracking the industry's climb up that IME ladder toward autonomy. This is where it gets really interesting. What's the first major milestone?
The first stop is 2030, laying the foundation. The goal is to get about 45% of key enterprises to that IME2 level of intelligence.
And what does success look like in 2030, in concrete terms?
For flexibility, modular software and hardware coverage has to be over 50%, so half the factory is reconfigurable. Operationally, OEE, that's overall equipment effectiveness, needs to be up 5% from today, and energy use needs to be down 10%.
Okay, so a solid start on efficiency. What about the brain, getting that embodied intelligence going?
This is the big one for 2030, closing that data gap. Data collection coverage must get over 50%, a huge jump from under 30% today.
That's a massive undertaking on its own.
It is, and the digital twin has to be fully functional with a crucial metric. The iteration rate must be hour level.
Meaning the virtual model updates itself based on reality every hour?
Exactly. Which is fast enough for basic prediction, but not real-time control. And the prediction accuracy has to be over 90%.
And for collaboration, how do the machines start working together?
By 2030, it's all about getting your own house in order, establishing enterprise-level data standards so your own machines can talk to each other. And the target for embodied robot application is over 20% in key roles.
Okay, so that's the foundation. Now let's jump to the midterm, 2035. Scaling intelligence.
By 2035, we're pushing for 30% of companies to hit IME3. Flexibility coverage jumps to over 80%. And we see the start of a true AI design ecosystem, where AI helps design the products and the processes to build them all at the same time. KPIs get tougher, OEE up 8%, energy use down 20%.
And the digital twin? That iteration rate has to get faster.
A lot faster. Data coverage hits 70%, and the DT iteration rate drops from hours to minute level.
Wow, from an hour to a minute. That requires a monumental leap in computing power at the edge.
It does. This is when those vertical large models running on cloud and edge systems become critical. Prediction accuracy needs to top 95%, and AI tools will start automatically adjusting tasks based on that minute-by-minute feedback.
And collaboration moves outside the factory walls.
Yes. The focus shifts to industry-level data standards, creating ecosystems where companies can start to share data and models to optimize the entire supply chain. And robot usage more than doubles to over 50%.
Which brings us to the end goal, 2040, achieving autonomy. The IME4 factory.
This is it. 40% of major enterprises are now at IME4. Flexibility is over 90%. Entire factory systems can be updated and reconfigured with over-the-air software patches. OEE is up 10% total, and that huge energy goal is met. Consumption is down 40% from 2024 levels.
Full OTA for an entire production line. That just completely changes the economics of manufacturing. What does the ultimate brain look like in 2040?
Data coverage is over 90%, and the digital twin iteration rate drops again, this time to second level.
Second level, so it's a true, real-time, closed-loop control system. Faster than a human can even react.
That's the goal. The equipment-side AI models are now powerful enough to run locally, with over 98% accuracy. And most importantly, the equipment can demonstrate true self-learning and self-evolution. It's not just following its programming, it's creating new solutions.
That progression hour to minute to second level iteration, that really is the core technological challenge of this whole roadmap.
It absolutely is. And for collaboration, the final step is establishing cross-industry data standards, linking automotive with energy, logistics, and materials. And robot application is now over 70%.
So given those aggressive targets, what are the specific breakthroughs we need to make this happen? Where are the biggest pain points right now?
There are critical gaps across all three pillars. Without breakthroughs, these targets are just dreams.
Let's start with pillar one, flexibility. What do we need there?
The main thing is cracking the code on software-hardware decoupling. That means developing new, high-performance industrial control chips that are designed for this kind of virtualization. We also need better AI algorithms that can automatically generate modular designs for a production line.
And for Pillar 2, embodied intelligence, the needs seem even more demanding.
They are. On the sensor side, we need to invent more durable sensors that can survive and stay accurate in really harsh environments. High temperatures, high pressures, corrosive chemicals.
What about the AI models themselves? You said they need to be smaller.
That's maybe the biggest challenge. We need to develop lightweight, large models under 1 billion parameters that can run efficiently on a small edge computer that requires total new ways of designing and compressing AI.
And security is still a huge piece of that.
Paramount. We need to get things like blockchain and homomorphic encryption out of the lab and deploy it at scale to build the trust needed for all this data sharing.
Finally, for Pillar 3, group collaboration and all those robots.
It comes down to standards and components. We need to agree on cross-industry data standards. That's as much a political challenge as a technical one. And for the robots, we need a major R&D push on their core components, motors, sensors, control algorithms, to make them more reliable and, frankly, cheaper, so they actually provide a positive ROI.
So, when you put it all together, this roadmap is painting a picture of a future defined by just relentless, high-speed computational evolution. What does this mean for a manufacturer or a tech developer right now? What should they be doing today?
It means the race from automation to autonomy is a sprint, not a marathon. The 2040 vision is this ecosystem of intelligent bodies that can reconfigure themselves on demand, operate with extreme reliability and efficiency, and coordinate across the entire globe.
Okay, that's the destination. But based on the analysis, what does the report frame as the immediate must-do actions, the strategic imperatives?
It lays out 3 of them, and they're pretty clear.
What's imperative 1?
Solidify the technological foundation. This is about strategic independence. It means investing heavily in the core building blocks. High-performance control chips, those specialized high-precision sensors, and open-source industrial software. The report is blunt. If you're relying on imports for these, you will always be a step behind.
So build your own tools, basically. Don't just buy them. What's imperative 2?
Establish the standard ecosystem. Data is the lifeblood, but without standards, it's just noise. The push has to be aggressive, from your own company's standards to industry-wide and then cross-industry standards. You have to build those data-sharing ecosystems because you can't get from single machine intelligence to group intelligence if all the data is trapped in silos.
Makes sense. You have to speak the same language. And the final imperative.
Accelerate scenario implementation. In other words, don't wait for the technology to be perfect. Start now.
Get your hands dirty.
Exactly. Prioritize pilot projects that will give you the biggest strategic advantage. The report points to modular design and digital twin integration as immediate priorities. And you have to start validating these disruptive technologies like embodied robots and those lightweight AI models in small, high-impact projects.
Right.
That's the only way you're going to generate the data you need to hit that 50% coverage goal by 2030.
So this roadmap is really framing this transition as a historic opportunity where global leadership will be decided by who can get to that second-level digital twin first.
It's a total strategic reset. The equipment is no longer a cost center, it's an intelligent partner. The companies that master this will control the future of manufacturing. It really is a blueprint for strategic dominance.
That's a powerful way to put it. And it leads us perfectly into the final thought we want to leave with you, the listener, today.
We've talked a lot about these timelines, about getting the digital twin iteration rate down to minutes and then down to seconds. So I want you to imagine this. If the machines are identifying problems, diagnosing them, and even repairing themselves at a speed faster than a human can even notice something is wrong, what does that mean for the role of the human on the factory floor?
Right.
If the machines have perfected the process, what new kind of intelligence, what new kind of strategic thinking will you need to bring to the table?
When the machines perfect the how, our job becomes entirely about the why and the what next. This deep dive shows us that the future factory isn't just faster, it's becoming sentient. And that's going to demand a new kind of human to work alongside it. Thanks for diving deep with us. We'll see you next time.